All right, well, I'm going to go ahead and get started. Last lecture, the topic is revenue maximization in multi-parameter settings. So let me just remind you, we had these 4 parts of the course where we were just obsessed with welfare maximization, maximizing the sum of the VIs. At the very end, I'm talking about maximizing the sum of the PIs, maximizing the sum of the payments to the seller. So if you like, we're thinking about the things from the perspective of some monopolists that wants to maximize their own revenue. Another thing I want to remind you is in the single parameter case, so this is where there's only one type of stuff and players' values are just linear in the amount of stuff they get. That was last quarter. Very well developed theory. That was Meyerson's theory, which gave us basically a very crisp understanding of optimal auctions. It's just maximize virtual welfare. And so the hope, what I want to talk about today is the extent to which we can get a multi-parameter analog of Meyerson's theory, this idea that revenue maximization reduces to virtual welfare maximization. And amazingly, there's been progress, significant progress on this issue just in the last few years, even though Meyerson's paper is from 1981. So that's pretty cool. Right, so, and then just why is it interesting? This is this theorem that in the single parameter world that revenue maximization reduces to virtual welfare maximization. There's both the sort of conceptual / structural. We have a good handle on what an optimal auction looks like. We know, for example, that even if you optimize over Bayesian incentive-compatible mechanisms, you get a dominant strategy incentive-compatible optimal solution. You get deterministic mechanisms as long as the distributions are regular. And then there's also the computational interpretation, which is, well, as long as it's a problem domain where you can maximize welfare, this automatically means you can maximize revenue too. Okay, because you just feed in the virtual values into your black box that maximizes welfare, and boom, you're done. You've got a computationally tractable revenue maximizing auction. So those are the analogs we're going to be striving for today, okay, for multi-parameter problems. Now, the main point of last lecture was to show, that that's a pretty ambitious goal. Okay, so we started with just these examples. We just had one buyer. We had 2 items. The buyer had an additive valuation over the 2 items, and its values for each were even IID from these super simple distributions. And already in that very simple case, the optimal auction could be really weird. Okay? And we showed that it varies a lot with exactly what the prior is, and we showed that, in fact, you may need randomization to be an optimal revenue maximizing auction. Okay? So it's no longer true that deterministic suffices to be optimal. Okay? You need randomization. So that's an important lesson that we learned. So we know things are going to look more complicated in the multi-parameter world, but still, even knowing that, we want to get as close as possible to sort of the holy grail of Meyerson's single parameter theory. Okay? So that's the context. Let me just remind you of the formal setup. So we're now not talking about just one buyer. We're talking about multiple buyers. So we're talking about auction or mechanism design setting. So we have items, M of them. And we're going to stick with additive valuations for now. Next lecture, we'll talk about unit demand as an example of how to push the theory further. But as we saw last lecture, additive valuations already pose a number of complexity. And we're working in the finite support case. Okay, so capital V sub I denotes the potential additive valuations that bidder I might have. And it has some density little f, and again, these are additive. So a bidder's value for a bundle S is just the sum of its values for the individual items J in that bundle S, okay? So there are these VIJs drawn from this prior. So just to be clear, I will be assuming throughout today that we have independence across bidders. Okay, so the FIs need not be identical, certainly, but bidder 1 and bidder 2, I'm going to assume that their valuations are independent. Some of the stuff I'll say extend to correlated distributions, but I won't make a big deal of it. Nowhere will we need that for a given bidder I, its value for different items is independent. Okay, so for a fixed bidder I, it can have an arbitrary correlated distribution over its values for the different items J. Okay, but independence between the bidders. Okay. So what we were talking about at the end of the last lecture was Right, so it was clear with all these examples we're looking at that it didn't seem like some nice closed form formula was going to be sufficient to talk about revenue maximization like it was in the single parameter setting. There's just too much complexity going on. So we needed some more sort of general tool for getting a handle on it. So we were looking at linear programming formulations, okay? And so we made the observation, although it wasn't really clear if it's useful or not yet, that the revenue maximizing auction for this kind of setup can be expressed as a linear program, a really big linear program, but a linear program. So the decision variables, so we have the revelation principle, so we can think about just direct revelation mechanisms. And so the decision variables of this linear program are going to correspond to the allocation rule and the payment rule of that mechanism, so X's and P's. So how would you write this? So revenue, well, so we want expected revenue, so we just average over the possible valuation profiles. And then we just look at how much money we make on a given valuation profile. Okay, so to be clear, F is given. This is just the given prior distribution. Okay, so these are just numbers that are part of the input. This is a decision variable. Okay, so this is the payment rule of our auction. And this is what we want to maximize, the expected revenue. Okay. Now, subject to what? Well, and this is going to be important to kind of remember this. There's three types of constraints in mechanism design. Okay, there's incentive compatibility constraints, there's individual rationality constraints, and then there's feasibility constraints on the allocation. So the IC constraints, and so remember, once you have more than one buyer, there's a difference between dominant strategy or Bayesian incentive compatibility, depending on whether it's a point-wise requirement or an average requirement. We're looking at the Bayesian incentive compatibility version, so the average version. So here, we just quantify over all bidders I, all possible true types VI, and all possible reported types VI prime. And again, this is just on average. Okay, so we average over all the types that the other bidders might have, according to the relevant density. And then, on the left-hand side, we say when we report truthfully, what's our utility? So we just do it good by good. So again, remember it's additive valuations. So I can just, okay, and so Xij, so this is the probability. Sorry, that should be Xij V bar. So the X's are our other decision variables corresponding to our allocation rule. This is the probability that bidder I gets item J when the reported valuation profile is V bar. And then there's the payments. Okay, so this is just the utility of bidder I total when the full reported value, reported profile is V bar. And then this is averaging over what V minus I might be. Okay, and that's how bidder I is thinking about it. Well, I know I'm VI, who knows what other people are. I just average over V minus I. Okay? And so this should be at least the same thing, yada, 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 yada. And then in here, of course, we still have the VIJs. Those are the true values. But then these things change to the reports. Okay? So those are the BIC constraints. And then we have the individual rationality constraints, which in this context are usually called interim individual rationality. And so this just says direct revelation always gives you non-negative utility, again, only on average. So this would just be the left-hand side above, right? So this is the expected utility if you report truthfully when you're V. So the left-hand side above should be non-negative for all bidders, whatever their actual value might be. And, but we're not done, right? So why do we need more? What other constraints do we need? It's one other set.
Feasibility.
Right. So like, which means?
Only one bidder gets an item.
Right. So there, we have these items. There's only however many there are, and each one should only go to one person, right? So they're simple, but we can't forget about them. Okay, so feasibility. So in every valuation profile, for every item, it should be the case that if we sum over everybody, that's the most one. Okay? So again, remember the semantics here are xij of v bar. That's the probability that I gets j on the input v. Okay, so the sum of everybody's probability should be at most 1. All right? So, so a couple things to remember. So, a special case would be a deterministic mechanism. That's when the x's are always either 0 or 1. But as we know, we need to allow randomization. So we're going to allow x's between 0 and 1. If you had a mechanism which was selling items separately, that would just say, x only looks at the jth components of this. Right? So remember what v is. So v, first of all, it's a vector of n valuation profiles, one for each bidder. And then for each bidder I, its vi is an m vector, its value for each of the m goods. Okay, so this is really n times m numbers that's being fed in here. Okay, and so one thing we saw is simple but not always optimal is just selling goods separately. That would just say, I'm not even going to look at the items other than j when I figure out how to allocate j. But as we've seen, in general, if you want to be optimal, maximize revenue, you can't just sell the separate items separately. You might want to bundle. You might want to do other things. So it's important that when you decide how to allocate an item j, you actually look at everybody's values for all of the items. Okay? So this is the general formalism. Okay? Oh, no, I guess there should be non-negativity constraints. Okay. So that's the LP I left you with at the very end of the last lecture. Let's notice it is, in fact, a linear program. Okay. So again, remember the F's are given. That's the prior. The V's are given. Okay, those are just people's potential valuations. And the X's and the P's are the decision variables. And everything is linear, the objective and all of the constraints. Okay? Also, there's certainly a correspondence between feasible solutions to this and mechanisms that we're talking about. A mechanism induces a feasible solution just with the intended semantics of the X's and P's. Similarly, if you look at a feasible solution to this linear program, it basically tells you what to do on every input. Right, so if you solve this, you get some X's, you get some P's, and evaluation profile V comes in, you just do like basically table lookup into the decision variables. You say, hey, what did the LP solve to for Xij on this valuation profile? Oh, it's 0.1. I guess I'll just give item J to bidder I with 10% probability. Okay. If you want, now you could ask, okay, how do you, how do you assign all of the items? It actually doesn't matter if you think about it. So from a player's perspective, because their valuations are additive and because they're risk neutral, all I care about are the individual marginal probabilities, the Xij's. So for example, you could just allocate each item J independently. That'd be one way to do it. Okay, go to item 1, look at the Xi1s, allocate randomly according to the Xi1s, repeat the process with item 2, repeat the process with item 3, and so on. And that would be a mechanism that would implement the intended semantics of a linear programming solution. Okay? And there's a correspondence, between the revenue of a mechanism and the objective function value here. Okay? So if in principle, if you solve this linear program, it would really print out for you instructions that would be a revenue maximizing BIC IIR mechanism. Okay? So that's kind of the straightforward approach. Okay. So there's some issues, all right, with this linear program. So you'd be right to ask the question, what have we accomplished? And let me remind you, why, when I said what we're striving for is Meyerson's theory, I tried to explain why we're so satisfied with Meyerson's theory. And there's two reasons. The first is sort of conceptual / structural. It gives us a handle on what optimal mechanisms look like, right? Virtual welfare maximizers. That's really nice. The second is computational. It reduces revenue maximization to welfare maximization. Okay? And this does neither of those, or at least not obviously, right? I mean, this linear program, so first of all, if all you tell me is that something is a solution to some massive linear program, it's not clear I've learned that much about it. Right? There's not a big takeaway there. Nothing like understanding it as a virtual welfare maximizer. Secondly, this is too big to be computationally useful. Okay, so notice that both the number of variables are indexed by the number of valuation profiles, and so are the number of constraints indexed by the number of valuation profiles. Okay, and that's a lot. Okay, so that's exponential in the number of players n. Okay, So it's not clear what we've done, although nevertheless, this is kind of the right starting point for more interesting results that I'm going to tell you about today. Okay? So what I want to do next is, and this, the exercise we're going to do next is kind of probably the most important takeaway for today, is we're going to try to basically have an equivalent linear program with much fewer variables. Okay, so the number of variables we're going to want to be only growing linearly with the number of players, not exponentially with the number of players. Okay? Now it turns out, so that hopefully seems like a reasonably good goal in its own right, but it also turns out that studying this problem of how to do this dimension reduction for this linear program will lead us to the structural insight that we wanted in the first place. Okay, so we will get to the conceptual payoff as well. Okay, but for now, let's just focus on, is there some way we could write down an equivalent version of this linear program with much fewer variables? Okay, so that's the next thing we're going to do. All right, so let me remind you of something that we just talked about very briefly. Okay, so I don't really expect you to remember it, but it's the notion of interim, allocation, and payment rules. The time we talked about this briefly is when I was first talking about Bayesian incentive-compatible mechanisms. We were about to talk about those black box reductions from approximation algorithms to mechanisms, and I did a special case in the single parameter setting. I talked about the extended Meyerson's lemma, and when we talked about the extended Meyerson's lemma, we were talking about the monotonicity of these things called interim allocation rules. So here's what they are. Let me remind you. So consider a direct mechanism, XP. Okay, so the allocation rule and the payment rule both take as inputs a full valuation profile. Okay, so in this case, a full n times m numbers from each of the n bidders. Now, any mechanism like this induces an interim allocation rule. Okay. And an interim allocation rule takes as input only one bidder's data. Okay, so only m numbers, not n times m numbers. And with the missing numbers, with the missing valuations, it just averages over the other n minus 1 bidders. Okay? So yi of vi is just the expected allocation that I gets when it reports vi, with the expectation over the unknown v minus I. Okay? So let me just also write this out in sort of the notation over here. So sum over v minus I times the probability of v minus I, of xi vi, v minus I. Okay. So in general, right, so the output here, actually, let me just go ahead and subscript this by j. Okay? So let's just talk about them separately for each item j. Okay, so for example, even if you started with a deterministic mechanism, okay, with no randomness, so x being always 0 or 1, now there is going to be randomness supplied by the unknown valuations of the other bidders. Okay, so even if it's a mechanism where you always either win or lose, you might still reason about this mechanism by saying, okay, well, if I bid $10, what's my chance of winning? Okay, where the chance is sort of the randomization of what other people are bidding or what other people want. Okay. So this would be the probability of winning in the case of a 0-1 rule. All right? And again, I want to point out it takes much fewer arguments, okay? Just that of one bidder, not of all n bidders. So similarly, although these will be much less important for us today, are the interim payment rules defined in the analogous way, where you just average over the payments of the actual payment rule, where you're averaging over the unknown v minus I. Okay? So any questions about that? Okay, so especially this one. Okay, so this is going to be, just this entire lecture on a technical level is about understanding this mapping between the x's and the y's. So the x's are what we're totally used to. I'll sometimes call these ex post allocation rules. Ex post in the sense that it's a function of the full valuation profile. Okay, so it's privy to all of the information of all of the bidders. And these are ex interim, where in some sense you only know VI and you're averaging over V minus I. Okay, so keep this in mind. I'll try to be consistent with the notation, where X is always the ex post rule and Y is always the ex interim rule. Okay, and so just a little more verbiage. So we're going to call YQ the reduced form of XP. Okay? So evidently, a mechanism XP induces a unique Y and Q. Right? They're uniquely defined. Okay? So, whoops. Yeah, so YQ is the reduced form. Y reduced, well, if you think about them as variables, notice there are many fewer sort of variables of the form YIJVI, okay, or QIVI, but especially here. So remember, X, it takes as an argument a valuation profile. Okay, so in some sense, the amount of data in X is proportional to the number of valuation profiles exponential in N. This is indexed only by the choice of the bidder, I, so N choices, M choices for J, and then the number of possible valuations for that bidder. Okay, so this, the amount of data of this form is scaling polynomially in the number of bidders and the number of items and the number of possible valuations. But the point is, this is not blowing up as the product of the number of different valuations of people. Okay, it's not indexed by the valuation profiles. So that's the sense in which it's reduced. There's much fewer of these than of these. Okay. Okay. The other thing you might expect, I mean, because in some sense we're compressing the information, okay, going from XP to YQ, you might have multiple different mechanisms, X1P1 and X2P2 mapped to the same reduced form. Okay, that's possible. All right. Now, why did we do this? So why did I introduce this? So remember, our goal was, can we have a smaller linear program? And so the question is, if we have a smaller linear program, what are the decision variables going to be? And so the point is, instead of the ex post allocation and payment rules, we're going to use the ex interim allocation and payment rules. And as we just argued, that's going to be a much fewer number of variables. The reason this works, okay, and this is sort of the big insight, is that almost, not everything, but almost everything we care about in this linear program can be expressed purely in the vocabulary of the ex interim rules. We don't actually need these sort of full-blown dependence on the valuation profile to talk about what we care about. In particular, to talk about revenue, that can be expressed in terms of the ex interim rules. The incentive compatibility and the individual rationality constraints can also be expressed purely in terms of the interim rules. Okay, we don't need all the other information. Feasibility is another question, and that I'll get to in a second. Okay, so key points. Interim allocation rules and interim payment rules sufficient to express expected revenue and BIC and the IR constraints. Okay, namely, so what do we do for the revenue? So by linear of expectation, we can just look at each bidder separately. We look at every type that bidder I might have. We look at the probability that it's going to have that particular valuation. And then we just look at the interim payment rule. So we look at how much we expect to collect from bidder I when it has the type VI. Okay? So that's an expression of the revenue now. Notice, none of this is indexed by a valuation profile. Okay? That's the key point. It's only indexed by the report of a particular player VI. That's the big win. So here we have V arrows, which means this is a sum over a zillions and zillions of things. Here we have a sum just over the sum of the supports of everybody's type distributions. So think of it as if like each player has 100 or 1,000 different types they might have. Okay, so think of the cardinalities of the VIs as 100 or 1,000. Over here, the number of summands here is, something like 100 to the n. All right. Here it's n times 100. Okay. Yeah.
So when we calculate the expectation
Mhm.
for QI,
Yep.
isn't that still over such an ugly space? Like how does the one do that efficiently?
So okay, good. So what's cool, so the payments work out really nicely actually, because bidders are risk neutral. Okay, so basically whatever randomness there is in the mechanism, I don't care. Whatever randomness there is in other people's types, I don't care. When I reason about like whether to bid 10 or whether to bid 20, under the assumptions that we have in this model, the only thing I look at is the expected amount of payment I make and the expected welfare I expect to get out of it. So the point is, so we're going to have this LP over here, and when we solve it, the semantics of the LP solution will say when this bidder bids 10, they should pay in expectation, 8. Okay? And now it's up to us as mechanism designers to figure out, so basically we're free to arrange the payment rule in any way we want, as long as at the end of the day, the expected payment of this bidder is 8. But so for example, they could pay $8 always, whether they win or lose. Now that's not individually rational after the fact, but with a risk neutral bidder, it's strictly speaking allowed. Or you can think about sort of ways to arrange the spread the payments over the space in some better way, in some more fair way, subject to keeping the expectation exactly the same. So the short answer to your question is we never need to compute this expectation. We'll just solve directly for the Q's. And we'll know there's some P's, but whatever. So yeah, good question. Other questions? Okay. So that's how we express the revenue, purely in terms of the interim payment rule. So for BIC, so what do we do? So let's see. Right, so now we just look at our expected utility. So when bidder I reports truthfully, it's expecting to get item J with probability Xij Vi. And again, buried in here is randomness both over V minus I and over any randomization in the mechanism itself. But again, the point is this risk neutral bidder doesn't care. Just cares at the end of the day, when I'm reasoning about what to report, what's the probability I get out of J? And because the valuation is additive, there's not even any complications about how the different items interact. It can just reason separately about the different items J, because valuations are additive. That's really useful. Okay, and then, this should be a Y, excuse me. Minus QI VI. Okay. So the point is, so this is bidder's expected utility when it reports truthfully. Okay? And again, the key point here is we were able to express its expected utility purely in terms of the interim rules. Okay? And then this should just be at most the same thing with the misreport. Okay. So this is BIC. And then for individual rationality, same thing. Left-hand side above. So the utility of direct revelation should be non-negative on average. And okay, so that's all I claimed. I claimed that the interim rules were enough to express expected revenue, BIC, and IR constraints. Right? And so I just proved to you. I just wrote them down. Now, okay, so let's try to think a little harder about feasibility. Okay, and these were already annoying constraints in the first place because this was the only set of constraints of which there were a lot. Okay, so you might even notice that the number, even in the old linear program, there's a ton of variables, but there are a small number relatively of incentive compatibility and IR constraints. Okay, again, proportional to the sum of the types. Whereas this was the one where really we had a constraint for every possible valuation profile. So the question is, how do we express this if our vocabulary is only the interim allocation rule? So notice the payments are totally irrelevant for encoding this. This is not about the payments, okay? So it's really about asking, how do we encode this constraint here on the ex post allocation rule using the vocabulary only of the ex interim rules, okay, using only the Y's. Okay, so, all right. So obviously we need to kind of throw in some constraints to enforce feasibility, So the question is, what should we throw in? So for example, it's going to be clear. Let me write down one thing, which is obviously a necessary condition. So again, this is going to be constraints that I'm supplementing this linear program with, trying to capture these constraints in our new reduced vocabulary. So it certainly should be the case that for every item j, so what I'm going to do is I'm going to look at a bidder I. I'm going to say just what's the probability that bidder I gets item j? Okay, averaged over everything we don't know, average over everything. So what do we average over? So we average over basically the types that bidder I might have, the probability that it has that particular type, and then I can just write down xij vi. So this is the probability that I wins j when its type is vi. Okay. So what's inside the parentheses is the probability that I gets the good. And if I sum over all the bidders, that should certainly be at most 1, right? Because the good can only be allocated once, always. Okay. Oh, this should be y again, sorry. So that's going to be true, right? So if you take any actual mechanism and you pass to its reduced form, you look at this interim allocation rule, it's certainly going to satisfy this inequality, because always it only gives the good away once. This is some average version of that, which might make us nervous. Okay? So the question is this enough, or do we need more? All right? So this is an issue, I mean, one, there's sort of a lot of formalism here, but two, I think you really appreciate the technical issues if you try to do one or two of these examples yourself. So I'm going to ask you to work on the following. It's about, these examples are like the complexity level of a ken-ken, basically. Okay, they're basically like little constraint satisfaction problems. So consider the following example. Okay, so the question is this also sufficient? So suppose there's 2 bidders, and let's just go back to a single item case. And let's suppose the bidders' valuations are just IID from some distribution F, 50, 50, 1, or 2. Okay, so there's 4 possible outcomes. All right. And suppose I gave you the following alleged interim allocation rules. Okay. So suppose y1 equals 1/2. And so again, don't forget what this means. So this means when bidder reports 1, it wins the item 50% of the time. Okay? Now, the other bidder, it might be 1, it might be 2. There's a 50-50 chance of each. Okay, so this is really an average over 2 outcomes. Okay? So bidder 1, all I know is I'm bidding 1, and I know the other person is 50-50, 1 or 2. Okay? And the mechanism is going to do something in either case. But if I average over both what the other player's value is and I average over what the mechanism does, this is my winning probability when I report 1. Okay, so and let's say that when bidder 1 reports 2, it wins with 7/8 probability. And let's say for bidder 2, it only wins 1/8 of the time when it reports 1, and it reports 1, and it wins half the time when it reports a half. Okay? So this is a mechanism that this seems to be favoring the first bidder for whatever reason. Okay? But whatever, that's allowed. Okay. So that's my question for you. My question is, does there exist an ex post rule X, that's feasible, that only allocates the good at most once, always, that induces Y? So I want you to think about that for a minute. Let me just make it clear what we're looking for. All right, so remember an ex post rule, so what are the candidates for X? Right, so when X takes as input a full valuation profile. Okay, so it's going to take in as input a possible value of 1 and 2, of which of course there are exactly 4 possibilities. And then the allocation rule has some probability of winning, assigns each player some probability of winning. Okay? So the candidates for X, for the X post rule X, are just ways of filling in these 8 squares so that every row sums to at most 1. Okay? So for each of the 4 reports, what probability do you give it to each of the 2 bidders? Okay? And so the question is there a way to fill in those 8 squares so that, for example, the average winning probability of the first bidder when it reports 1. Okay, so these are the 2 cases where bidder 1 reports 1. So this is the probability that the mechanism assigns to bidder 1 in those 2 cases, and these are equally likely. So the average of these 2 numbers should be half. Okay, and there's 3 other constraints of the same form. So is it clear what we're looking for? Okay. So if you think you've figured out a solution, shout it out. If you think there's no solution, explain why. Oh, I should say, this does meet the sufficient condition, or the necessary condition. Okay. So the necessary condition, so how would this work? So in this setup, this is always a half. Right, so everybody's equally likely to get either type. So this is just the sum over all of the y values multiplied by a half, and the y value is indeed summed to 2. Okay, so this is legit for this constraint. Yeah.
I don't think you can do it.
Okay, how come?
Because I think the upper leftmost one has to be 4/5, and then the upper rightmost one has to be 1/5 to satisfy the 1/2 and 1/8, the column.
Well, the 1/2 and 1/8.
So like, if they both report 1, doesn't the first bidder have to get it, ratio 1/2 to 1/8 of the time? No.
Yeah, it's tricky, right? Because there's the profile 1, 2 is relevant for this quantity, and the profile 2, 1 is relevant for this quantity.
Okay.
Yeah. But this is the right kind of it really is like, it's very Sudoku-like, I gotta say, this exercise, so. So I'll give you like 30 more seconds, and then I'll tell you the answer.
Maybe in those 30 seconds you can give me like a quick speed up.
A quick what?
Speed up.
Talking about revenue maximization again.
Yeah, but so what do these constraints mean?
We have new interim allocation rules, and then secondary rightmost line. So instead.
What do you think?
Let's suppose we just look at the left column. So we have that the first 2 numbers must add up to 1, right?
Let's see, because we have a half here.
Right.
Yep.
And the second 2 must also add up to 1.
Because we
the 2 in the
have a half here.
The 2 in the bottom
No.
right have to add up to 1. Therefore, the 2 in the bottom left also have to add up to 1.
Oh, I see. You're saying the column sum. No, hold on. So
The bottom right thing indicates like they're not the bottom 2, right? They're like 2 alternate ones.
So I agree. These need to sum to 1. What inference do you want to make here?
There's also sum to 1 because the 2 in the bottom right have to sum to 1.
And why is that?
Because of the white 2, 2.
Because of this.
You have to move one of those up.
I think it's these have to sum to 1.
Oh yeah, that's right.
Yeah. So those sum to
Okay, so
1.
those sum to 1.
Yep.
And then we have y1, 2 equals 7/8, which means that the
Yeah, I guess, yeah, one hint is that the extreme numbers tend to be helpful. Things close to 0 or 1 tend to be helpful for solving these problems. So you're saying the 7/8.
yes, that means that the 2 things that end with 2, the second and fourth.
That's about these 2, right?
Oh.
Y12 refers to these 2 things.
Oh, okay, yeah.
Right, so those should average to 7/8.
Yeah.
Right, so this sums to, right, okay, good.
So I think we can take the 1/8 and we can move that into an average of 7/8 on the other side. Because, so we can figure out that two things on the right add up to 1/8, add up to 1/4, right? Which means that the things, corresponding things on the left would have to add up, would have to have an average of 7/8.
Okay, my guess is, I mean, this is exactly the right kind of reasoning. So my guess is if we actually wrote down all these constraints, it would force us to the following numbers I'm going to write into the table. But I think I'm just going to write them in now. So, but I mean, that's exactly how you reason about it, right? So basically, you know, you have constraints on pairs. So certain pairs have to obey certain averages. And unfortunately, you can't pair up the pairs easily. It's more like this path, this directed path you have to chase around, but eventually you get implications backward. Is that a hand or?
Maybe, sure. Yeah. I think I have one.
Okay,
Um,
what do you think?
So I think 1 there, where are we now? Or well, 0 to the right, I'll say. Then 0 to the, yeah, going back.
Here?
Yeah.
Okay,
And then 1. And then 3/4. And then to the right, 1/4. And then 1/4, 3/4.
You should finish with 1-0, I think, in the bottom row.
Yeah, I could be wrong.
Some of the ones in the
Bottom
left
row
bottom
should
should
be
be
1-0, I think,
7/8, right?
and then everything one.
so if the bottom one is, you're saying this should be different?
I think that should be 1-0, yeah.
1-0.
No, some
One.
of the ones on the left side should be like 7/8, right?
7/8, yeah.
No, so the average should be 7/8.
Is it 7/8?
That?
So now it's 7/8, because 3/4 and 1 now average is 7/8.
Well, no, that definitely doesn't work.
This, why doesn't it work?
They were
1,
fine
2.
This works, right? So a bunch of like things.
Wait,
Which one, this might work actually.
Yeah, this.
It's not the planted solution I have, but,
So it's not unique, right?
Sorry?
no, there's no reason to think they're unique. I
You
agree.
get like this cycle, and then you can just pick anything that works in a range.
Yeah. So this seems fine?
Yeah, this
I
seems.
think this one holds.
Okay.
wait, this,
Oh, I think I misread the thing.
This looks good to me.
Yeah, that's fine.
I think it's good. Yeah.
I misread it.
Yeah. Good. Okay. So here's an easier one. So example 2, what if I'll keep the 7/8 1/8, I'll make that 1/4, and I'll make that one 3/4.
Would you ever have Ys and not X's?
What do you mean?
Like, would you ever,
Yeah, this case you have Y's and no X's. right?
yeah, I'm wondering like when, don't we make the Ys, well, I guess we don't have. I'm wondering when we try to make X's from Ys, I guess.
So the point is the X's are just too big.
Yeah.
Right, so the high level thing we're doing is we're doing this dimension reduction.
Yeah.
So what we want to do is we want to sort of in our mind have the X's there, right? And the X's actually correspond to actual mechanisms.
Yeah.
But we're doing this sort of compression, we're passing the interim rules, which is a small enough set we can kind of do things like compute on it.
Yeah.
And I'll show you later that we get other conceptual insights from working with the Ys. I haven't yet, but that's a promise. And so, so what you'd like to do is, you know, compress to the Ys, do computation on the Ys, and only at the end, once you've optimized over the Ys, do you kind of back out what's a good X corresponding to the one Y.
Ys don't actually give you a mechanism.
Well, that's exactly what we're trying to study. We're trying to study which Ys correspond to a mechanism in the background and which don't. Now, even if you have Ys that do correspond to some mechanism, there's a question of how do you find it. And I'll mention that a little bit at the end. But it can be done. Yeah. So what do you think about this one?
This one's not possible.
How come?
So there's a 1/2 chance that you get paired, like the Y12 case gets paired right, with the y22 case,
Yeah.
and y1 chance vice versa. So the y12 case needs to win at least 3/4 of the time
Yeah.
against the other two.
Yeah.
And the bottom needs to win at least 1/2 of the time, but that adds up to more than one.
Yeah. So basically, the problem is kind of what happens on the profile 2-2. Right, so both of these are high. I mean, this isn't a total proof, but this is the idea of the proof. I mean, this says that, when the first bidder bid's high, it should usually win. This says when the second bidder bid is high, it should usually win. Right, but sometimes they're both bidding high, right? And, one of them is going to win with probability at most 1/2. Right, so that's a problem. Okay? So this is infeasible. Okay? All right, so why did I do this? I did this for a few reasons. One is, this problem of understanding which y's are feasible, which y's correspond to bona fide x's, is like the main kind of technical core of this lecture. So it's important that you really understand the issues around that problem. That's the first reason I did it. The second reason is, when you play around with it, you appreciate that it's not a trivial problem, right? So this, somehow, I think what is clear from playing around with it is it's some linear system. Right, so basically we're just saying that certain averages in this table should be certain targets. Right, so if you wanted, we could write down a huge linear system, and that would characterize whether or not it's feasible. Would say whether or not there's a x corresponding to the y. So that's the second reason. It's a complicated mapping. Third is that it's important to now understand that this is not enough. Okay, so our second example shows, and again, notice the second example still satisfies this necessary condition. Okay, because these numbers all sum to 2. Okay, so the linear program we have written down right now, this stuff over here, plus these single extra constraints for the individual items, this is not good enough. There are feasible solutions to the linear program that's currently on the board that do not correspond to mechanisms. Okay, there are y's that satisfy these inequalities for which there's no x that projects to them. Okay, and that's not okay, because we want to do things like optimize over the y's to find a revenue maximizing y. But then if we did that and there was no corresponding mechanism, it wouldn't do us any good. Okay? So the final point is just this is not good enough. We need to add further constraints. Okay? So we're not going to give up, but we just have to add more constraints. All right? Okay, so point. It turns out we need to add a lot more constraints. Okay? So we need to add more constraints to ensure feasibility. Okay, and so by feasibility, I just mean that every y that's a solution can be mapped back to a mechanism for the original setting. Okay, so here's what's going to happen next. So in the remainder of this first lecture, I'm going to explain how this gets done for the current setting that we're talking about. So I'm going to give you basically a complete solution to what are the extra constraints that force every y to correspond to some x, okay, for additive evaluations. And that's where then we're going to take a break. In the second lecture, we're going to do a few things. So first of all, we're going to go beyond additive evaluations. We'll talk about unit demand valuations also. That'll be clear that really the discussion's more general. And then, but it's not so much that we want to capture unit demand valuations per se. It's going to be that looking at this feasibility issue more generally will lead us to the structure of optimal mechanisms, which is really kind of the main point of today. Okay? But so first, let me just tell you exactly what constraints are necessary and sufficient for additive evaluations for every y to correspond to an x. All right, so let's look at so here is one necessary condition. Let me show you actually a bunch more really easy necessary conditions. So we can treat each item separately. Right, so we have xij's and we have yij's, and just with respect to feasibility, different items don't interact at all. So we're just going to sort of handle each item j independently. And so suppose we had a bona fide ex post allocation rule. Okay. And consider the induced interim rule. Okay, so I'm going to write down some inequalities that these y's will certainly satisfy. Okay, okay, if you started from a real allocation rule X. So for simplicity, I want you to think of, all right, so remember we have these capital VIs. So capital VI is the possible valuations that a bidder could have, $1, $2, $3, and so on. So these are these different sets. I want you to think of every element in these sets as disjoint, okay? That's just convenient. So think of it as if it's also tagged with the bidder's name, okay? So I'd have a type that'd be like, my name is Tim and I'm willing to pay $10. That's actually my type, okay? And then everyone else here has a different one tagged with their name, okay? So without loss of generality, so that obviously affects nothing. It just lets me write unions in ways that's not confusing. All right, so now, it's going to be a lot of different conditions. Okay, they're parameterized in the following way. So for bidder 1, of all the possible types it might have, pick your favorite subset, I don't care which one, S1. Do the same for each of the other bidders. Okay? So I'm going to write down 2 quantities. It's going to be obvious that the second one's at least as big as the first. So expression 1, right, so remember, so there's this fixed allocation rule in the background. So imagine I run the allocation rule, X, okay? So I pick a random valuation profile according to the prior. There's some prior also. I should say that. So fix F. So I pick a random valuation, and then I look at who wins, if anybody. And I'm looking at the probability that the winning bidder under this allocation rule X has type in one of these sets, okay? So if the winner is nobody, then it doesn't happen. If the winner is bidder I, then it counts if and only if bidder I's type is in SI, valuation is in SI. Otherwise it doesn't count. Okay, so probability that the winner, right, so the probability is V drawn from F, and also under any randomness in the allocation rule, if there is any. So winner, So winner of item J in X bar in X on V has type in the union of these SIs. Okay? And let me just point out this is easy to write as an expression as a linear expression of the interim allocation rules. Right, so what's the probability that the winner of item J has type in some SI? Well, by linear of expectations, we just look at the bidders separately. If we're talking about bidder I just look at the various types it might have that are indeed in S sub I. I look at the probability that I has that type, and I look at the probability according to the interim allocation rule that it wins item J when it has that type. Okay? So that's quantity 1. Again, the F's are given, that's just the prior, so this is a linear function of the Y's. Okay? So here's the expression which is obviously bigger. So let 2 be the probability that one of the bidders simply has a type in an SI. And again, this probability, this has nothing to do with the allocation rule, of course. So this is just for a random valuation profile drawn from the prior. There exists a bidder with value in the set capital S sub I. Okay? And so if we wanted to write down an expression for this, so this is 1 minus the probability this doesn't happen. And this doesn't happen if everybody misses their set SI. Okay? So this has nothing to do with anything. This is just a number. Once you fix the prior, this is just, 0.1, whatever it is. Okay? Now, what I hope is clear is that 1 is at most 2, no matter how I choose these restricted sets of types. Okay? So if you parse the definitions, that's clear. Right? The right-hand side is somebody has a type in SI. The left-hand side is not only does somebody have a type in SI, but also such a person 1. Okay? So it's a more restrictive condition. The probability is only smaller. Okay? So 2 is at least 1 for all choices of restricted types. Okay? So something which is maybe kind of surprising is that, okay, so again, remember what this is. So it's going to be true that any, right, so again, this is just a number. So think about this as a constraint, okay? So so again, the prior is fixed, so the right-hand side is just a number, 0.1. The left-hand side here is a linear constraint on the interim allocation rule, on the y's, okay? And the assertion is just that if y is derived from an x, so if y is a legitimate interim allocation rule, then this is true for all SIs, okay? So what I want to tell you about next is Border's theorem, which states that the converse is also true, okay? So you give me some y's, an alleged interim allocation rule. The claim is that if these constraints are satisfied, so again, remember, right-hand side is a constant, left-hand side is a linear constraint on the y's. So if your y that you give me satisfies these for all choices of the S sub i's, then what I'm going to prove is that there is indeed an x that induces that y. So y is indeed an interim allocation rule. Okay? So it cannot be an example like this. So if you, put differently, if you give me a y like this one, which is inconsistent with every x post allocation rule, then it must violate some constraint of this type for a suitable choice of the SIs. Okay? So not only are these necessarily holding for every interim allocation rule y, they characterize the interim allocation rules y. Okay? So is it clear what I'm stating? So that's Border's theorem. That this is also sufficient. So i.e. Yij vi's induced by some xij v arrows if and only if 1 at most 2 for all S1 in V1, Sn in Vn. Okay? All right, so I'm making good progress. So I'm gonna prove this to you because I like the proof. The proof is basically something you'd put on a 261 final. The proof is max flow min cut. Okay? Took a long time for economists to realize the proof was max flow min cut, but now we all realize that. Okay? So, all right, so maybe I'll show you the network. So we're thinking, the way you should think about it is that we're given the y's and we're trying to compute, we're not worried about efficiency, but we're going to use max flow. We're trying to compute on a big graph using max flow a suitable x. Okay? That's what we're trying to do. So it's just going to be a simple 2-layer network with a source and a sink. So in the first layer, we just have all of the possible evaluation profiles. Again, remember, we're not trying to do anything efficiently here. We're just trying to prove something. Okay? Okay? So I'm going to write down this big graph. So there's a valuation profile, there's another valuation profile, and so on. Okay? All of these have arcs. And flow in this graph is going to correspond to probability. Okay? So we're going to try to push 1 unit of flow from S to T corresponding to probability. So given that so we think of 1 unit of probability starting at S, and then it goes to the valuation profiles. And so, the capacities on these arcs out of S are what you'd think they would be, right? So we have a prior. It tells us exactly how likely each valuation profile is. We just use those numbers in the prior to assign capacities on these arcs. Okay. So this is just F of V1, F of V2, and so on. Good. So now remember, so we're thinking of we're given as input the y's, and we're trying to now compute the x's. So x is a full-blown x post-allocation rule. It has to decide what to do for every valuation profile, okay? Meaning who wins, okay? And again, I'm just doing this separately for each good. So think in your mind that there's a single good, and now basically flow coming out of a valuation profile is just going to say who's the winner. Okay? Or if it's sending flow to multiple people, that's like a randomized decision about who the winner is. Okay? So the next layer is going to be these tagged evaluations. So think of it as, we have, so this means that player 1 wins when its type is V1. This is player 1 wins, when it has some other type, V2, and so on. And then down here we have player N winning when its type is whatever it is, V sub L. And then we also have a dummy node for nobody wins. Okay? And these are all going to be connected to the sink. And remember, we're given the interim allocation rule. Okay, so we're given these y's. And y says exactly this kind of information. It says when a bidder I reports a given type, the probability that it wins. Okay? And so basically on one of these outgoing arcs is going to be just y. There's going to be y of 1 when its report is V1. There's going to be y of 1 and when its report is V2. Y of n when its report is VL. And then this just basically has all the residual, this last no sale arc has the residual probability. So these things are going to sum up to something that's at most 1. That was basically the necessary condition I just erased. So whatever the extent to which this is less than 1 is just what we put up here. Okay? So the sum of these, of course, are 1. So the capacity incident to the S, the capacity incident to the source is just equal to 1. And then over here as well, the capacity incident to the sink is equal to 1. Okay? And then inside here, from each valuation profile, right, so this says who the n bidders are and what their types are. There's n plus 1 outgoing arcs. The plus 1 is because the mechanism always has the option of having no winner at all. The n types, well, you can award it to bidder 1 or bidder 2 or bidder 3. You have those n options, but of course, you can't choose what their type is, right? So given a valuation profile, either you can award it to bidder 1 when their type is V1 or bidder 2 when their type is V2, and so on. Okay. Oops, yeah, so that wouldn't work. All right, so you have an outgoing arc to only one node that represents bidder 1, and it's exactly the node where bidder 1's type is what its type is in that valuation profile. Okay? And we're going to go ahead and make these infinite capacity because we can.
One is also infinite, I suppose.
Yeah, infinite, I mean, it just helps us reason about the proof, right? So ultimately, we've got to say that every cut is big. And if some of the things are infinite, then if you cut one of those edges, we know it's big. So we're making our lives easy here. Okay? So that's the graph. All right, and so claim 1 is that the y's, okay, so remember we're given the y's and our job is to check whether they're feasible or not, whether they're a real interim allocation rule or just some poser thereof. So the claim is that there is an allocation rule inducing the y's if and only if this network supports a flow of value 1. Okay? If it supports a flow of value 1, then again, think of basically a flow in this graph is an explicit description of a mechanism, right? So given a valuation profile, you just look at the outgoing flow, you scale it back up by the amount of flow that was incoming, and that tells you the probability to award the item to each of the people, okay? So I'll leave that for you to check offline if you like. But I've set up the graph so that flows of value 1 correspond exactly to ex post allocation rules that induce the interim rule y. Okay? So that's what it boils down to. Does this network support a flow of value 1 or not? So that, of course, by max flow min cut reduces to just checking that every ST cut has value at least 1. So that's what we're going to do. Okay? All right. So let's say you check y induced by some x if and only if max flow value equals 1. Okay, so in fact, flows of value 1 correspond to ex post rules x that induce y. Okay? So, by max flow min cut, just need to check all ST cuts have value at least 1. So fix an ST cut, and I'll draw a picture. So the schematic that I want to think about is this first layer is divided into some A and some A bar, and this second layer is divided into some B and some B bar. Okay? So A and B are on the source side of this cut. All right, so what edges are cut? Okay, so again, remember, the source side, so the source side here is this. So all of these edges sticking into A bar are cut, at the very least, and all these edges sticking into T from, no, sorry, that's not what I wanted. All the arcs sticking out of B into T are cut. Okay? So I need to relate this to this condition, relating 1 and 2. Okay? So the claim is that as long as these conditions 1 at most 2 hold, then indeed the min cut value is at least 1. Okay? But I mean, I need this, right? We know that y's, if we don't have these extra constraints, then there will be y's that we can't implement. Okay, so here's what we do. So we define S sub I to be the types of I, or the valuations of I, that are not represented in A. Okay? So evaluations in S sub I if every single occurrence of it is in A bar. Remember, these are valuation profiles. Right? So in each profile, I has some type. S sub I are the types that only appear in the valuation profiles in A bar. Okay? So types of I not represented in A. Okay? All right, so that tells us something about how much capacity we're cutting here. Right, so remember, we cut every arc that goes from S to a type in A bar. Okay? And again, remember, by definition, every single occurrence of S sub I is down here. Okay? So here's the first key claim, which is straightforward if you can just keep track of all the notation. So the total capacity of the cut edges between S and valuation profiles, these are valuation profiles, is at least the probability that there exists I with a type in S sub I, which was exactly our expression 1. Okay? So again, this is just by how we defined S sub I. All occurrences of everything in S sub I are down here. Okay? So in any valuation profile where anybody has a type from SI, that's got to be an A bar. Okay? An A bar are the things that are getting cut. Okay? And then the sum of this is just the total probability mass on those events. All right, so we cut at least 1 right here. Okay? So now here's where having infinite capacity edges simplifies our life. So I've drawn edges going both into and out of the red blob, right? But one of those we're not going to have. Which one? So see these two crossing edges? I claim one of those we'd immediately be done. We're trying to prove that the cut has value at least 1. Yeah, so forget this one, right? That would be a cut edge of infinite capacity. This thing going in is fine. Okay, minimum cuts won't have those, but that's fine.
One question, the cut from S to A bar, shouldn't that be 2? Why is it 1 instead of 2? 1 was the probability that you have it in SI and you win. And 2 is just the probability that
Oh, that's 2 maybe is what you're saying.
yeah.
Oh, sorry. You're totally right. Thank you. Thank you. You're absolutely right. Yeah, absolutely right. Yeah, good. Okay. Yeah. That's a 2, Tim? Jeez. Sorry. It's an unusually thin 2 for me. All right, so what does that mean? So what does it mean that we don't have any outgoing arcs? Well, so that means, right, so, all right, okay, let me just write this down. So I can assume that B includes every arc of the form, right, so every node of the form IVI with VI not in S sub I. Okay, so consider a valuation which is not an S sub I. That means it is represented in A, right? That is, if you're not an S sub I, there's some valuation profile here where indeed bidder I has this valuation V sub I. That means there is an arc to the node which represents I winning at a valuation V sub I. Okay? So that node better be in the set B. So that's all this says. You can assume B includes every node corresponding to a bidder I winning with a valuation VI when VI is not an S sub I. Okay? So else cut a plus infinity edge. And now remember, we cut all of the arcs out of B going to T. Okay? So total capacity of cut edges of the form IVI to T is at least, so remember the sum of the capacities here is 1. So it's at least 1 minus the stuff I don't cut. The stuff I don't cut is here. And all of the nodes here have the property that VI is in SI. Right? So any node where VI is not in SI is up here. So these are only nodes where VI is in SI. Okay? So 1 minus, yeah, let me just write down the capacities. So I sum over all of the bidders, I sum over all of their possible types in SI, and then I look at the, I get this right? FI I see. I apologize, I made one error on this capacity. So y1 of v1, that's the probability, right, so the way I define this doesn't sum to 1. I got the scaling wrong. So y1 v1, so that says when bidder 1 has valuation 1, the probability that it wins. Okay, so it's the probability it wins conditional on having the valuation v1. So the unconditional winning probability and having v1 is f of 1 times v1. Okay, similarly this would be f of 1 v2, and this would be f of n vl. Okay? So I wrote down conditional probabilities of winning given your type. What I really want is just unconditional event that you both have a type, a certain type, and you won at that type. And now these sum to 1. So sorry about that. So now I'm just summing up the capacities of the cut edges over all of the nodes where bidder I has some type in S sub I. And so that's F sub I, V sub I, Y I, V I. And this is equal to 1. Okay? So that's just the probability, right? Or put differently, this is the probability of a winner, both, it's probably the winner is a bidder I with a type VI. So adding them together, so cut value, what did we decide? It's at least 2 plus 1 minus 1. And remember, the assumption is that 2 is at least 1. Okay? And that was for an arbitrary ST cut. Okay? So every cut has value at least 1. It can support a flow of value 1, so that gives us the allocation rule implementing that Y. Okay? So again, before we break, let me just remind you why we were doing this. Right? So this completes, something nice. So we had the super big LP with exponentially many variables. We asked the question, could we have a smaller LP expressing the same thing? And so we decided on the variable set very early. We said, well, let's just have a variable for each, for the interim allocation rules and the interim payment rules. And then there was a question, could we actually write down a set of constraints phrased only in terms of the interim rules that captured the full mechanism design space and no extra stuff? And it was easy to capture the BIC constraints. It was easy to capture the individual rationality constraints. It was easy to phrase the objective. So Border's theorem now says, if you just stick in these 1 at most 2 constraints for each of the items J, and again, remember, these are written purely in terms of the interim rules Y, okay, so they're in the right vocabulary. You throw all of these constraints in, then now we have the LP we want. There's a lot of constraints, but at least there's a poly-size set of variables, and everything in there is the mechanism design feasible region. Okay? So let's break for 10 minutes. When we come back, we're going to generalize this, and the payoff will be finally we'll get an analog of Meyerson's theory for these multi-parameter problems. We'll discover a sense in which optimal mechanisms, while not virtual welfare maximization, are just distributions over virtual welfare maximizers. So that's what we'll study in the last lecture. So see you in 10 minutes.